School of Engineering. Okay, so Lee, let's have Lee. Lee here is going to tell us about an event. Yes. No, it's fine. Go ahead. Can we get the slides? Here we go. All right. Beautiful. Here we go.
Yeah, so a week Saturday we have Drupal Camp Chattanooga. It's our 4th year. We hold it at Chattanooga State. Yeah, 4 years. I can't believe it. If I'd known how much trouble this was, I'd have never started. So tickets are $25, lunch T-shirt. We've also got a full Drupal 8 training in a day. Drupal 8 just came out. It's an entire sort of back-end rewrite, all in Symfony and Composer. The modern PHP. It's not your dad's PHP. It's not written like a lot of the stuff out there. And of course, we have a big after party. We got a guy from Lullabot, Mike Herschel. He's the guy who built sci-fi.com, which is a Drupal site. And we've got Doug Van, who's, we like to call him the Drupal trainer to the stars, because he trains NASA. So the guys at NASA use Drupal all over the place, and he's one of their professional trainers. So he's down here. There's other sessions, but the beginner session, or if you're interested in trying out Drupal or seeing what it will do, then this is where to go, because you will go from nothing to building Drupal websites in a day. And of course, we have an after party, because we should. We got beer from Smith's Basement, and that's just a bit of the fireworks we're letting off, because it's the 5th of November. And it's Guy Fawkes, so we should let fireworks off. And luckily, it rained last night, so with any luck, the burn ban's over. So we have sign up on the site, not with the admin stuff on it. So I'd love to see you all there. Support all the local sessions. Yeah, and that's it. So anyone that's interested, it'd be a good time to come and have a look.
And Alex, come on up.
Hey everyone, I'm Alex Cruikshank from Carbon 5, but I also do art dev on the side, and art dev is getting together with the Enterprise Center, Causeway, a few other organizations to do an event called Toyvention. It's an event where we're going to, basically we're getting a bunch of toys and we're going to take them apart, modify them, put switches on the outside, and we're going to give those toys back to the Signal Center. Signal Center works with disabled children, children that don't have full motor control, like can't really play with electronic toys the way that most kids can. And so the goal here is to create a bunch of toys that these kids can play with. It's actually very important for these children to be able to kind of learn cause and effect. They don't always have, basically when your muscles don't move the way that you think they're going to move, it's like a little bit, it actually causes cognitive deficit. So like being able to play with these toys is actually therapy for these kids. So I think it's going to be a great event. We're going to learn some soldering skills. We're going to learn some other making skills. We're going to be taking toys apart. We're going to be putting them back together. It should be fun. There's going to be food. And so what we're trying to do is there's actually two parts of this. There's a Indiegogo campaign to buy the toys. So if you're interested in just supporting, you can donate to the Indiegogo campaign. It's just go to Indiegogo and type Toyvention, and you'll find that campaign. $20 buys a toy. The other thing you can do is show up on November 12th, and that's what I'm really here for you guys, because I know you guys are all probably have done some of this before, and fairly technical. So it should be fun. We're just going to be just cutting the toys up, soldering things together, making new switches for them, and there'll be a lot of people that day. So if you could come out on November 12th, there's you can go to theedney.com/Toyvention and find the Eventbrite. There's an Eventbrite for it. You can also just go to Eventbrite and search for Toyvention and find it that way. But it's going to be here. It's going to be on the first floor here, and we're going to be here all day on Saturday. Well, not all day, but like something like 10 to 3. And so there's like times you can sign up for, or you can just come for as long as you want to, and make as many toys as you can. So anyway, thank you.
Great pitches. Okay, so Lee here is a remote software engineer. He's worked for NetGeo and the Washington Post, and this project was actually a project that he's dusted off for us. And he's actually driven down all the way from Jonesborough, Tennessee. It's about a 3-hour drive. So we're always glad to have him. This is his second time here. Glad to have a repeat offender. And yeah, so you guys give it up for Lee.
Am I working now? There we go. I hear myself. Well, thank you guys very much, first and foremost, for letting me come back again. Obviously, I didn't do horrible. Brett still let me come back for a second time. I apologize in advance. I'm chewing gum to keep from coughing. You can kind of hear, I went for a sunrise hike earlier this week, and I guess the dry leaves or something has set off my allergies. So bear with me, and I apologize. I've got some water, and I'll try not to cough in everyone's ears. As Brett already touched on, I used to work for the Washington Post. When I left there, I was a senior developer, and I've kept in touch with people there, and so has my previous manager. He's now at UNC, and he teaches new media journalism classes and technology for journalism. And so the Post reached out to us last year, and they said, hey, we want to do something really cool and interactive, new media tech for the White House Correspondents' Dinner. So when you go into the hotel, the Washington Post has a huge reception area, and they went all out. And we'll get into pictures of that later. But they built like a 7-foot-tall model of the dome. And what you see here is a wireframe of the 3D model that we have, and that's the dome on the Capitol building in DC. And they're currently renovating that. So they did a lot of interactive media and information around the renovations taking place, because that's a very iconic thing in the DC area, and it was all of a sudden covered in scaffolding. So the structure of this talk is actually more of like an introduction to Three.js. I was on the Slack channel. I asked a few questions. What do people like? I'm sure someone here knows way more about Three.js than I do. But quick show of hands, who's used Three.js before, knows what it is? Not too many, okay. Well, that's good. Just like I said in my last talk, most of you won't know when I'm lying. That's super important. There's a lot of content to cover, and it's a very short amount of time here, so there's no way we're going to be able to cover everything in depth. If you have a burning question, shoot your hand up, yell out, Lee, hey, man, and we'll do the questions as we go through. Otherwise, hold on to them at the end. I'm happy to demo, and everybody can come up and play. I've got a Leap motion controller. We're going to talk about what that is. It's like a Kinect. It's got dual infrared cameras. We'll get into more details there. Basic structure of the presentations, we're just going to layer things up. We're going to talk about a foundation of Three.js and how that works within a browser, and we can talk about why we used a browser for that. And then we'll demo the Leap motion, and then we'll demo the project that I built. Word of caution and a brief disclaimer. This is in no way a tutorial. Again, I'm not an expert in Three.js. I just have some lessons learned that I wanted to share, and as far as I know, I've not talked to anyone else that's kind of done an integration with the Leap motion controller like we did. So there's some pain points and things to look at there and see what the code looks like. But for the most part, it's very plug and play. So if any of this interests you, please look on 3js.org. There's other resources out. If you just Google 3JS tutorial, you'll find a lot more authoritative information than this presentation. Just so we all are on the same page as we go through the presentation, there's a really quick 3D primer. How many people know stuff about 3D graphics? Great, that's most of the room. Excellent. So we're going to talk about our scene, which is our collection of objects. What you're seeing on the screen there, we have an example scene set up. That little white box is a directional light. The red cube's just a standard geometry cube. There's no subdivisions for technical folks here. The green thing's just a plane. Again, no subdivisions. These are all triangulated polys, and this was put together in the interactive editor that's offered on the Three.js website. So this is actually like you can interactively play with Three.js stuff if you go on their website. So those are the basics. There's a lot more technical info in the notes. These slides are already up on SlideShare. I can post those in the Slack or on the Meetup. But we'll do the very first steps here, and what we're doing is I basically copied, there's a they don't call it getting started, but there's a getting started section in the documentation with Three.js. And so I've copied those over, and we've got those to look at. So we're going to step through, and I've made some mistakes on purpose, and we can talk about the correct way to fix some of these things, the side effects of fixing them, what looks like a solution might not be a solution, and we'll touch briefly on lights and shadows. Those end up being, they're not hard, but they're something to stumble upon. So our brief Three.js example that we're going to start with, we're just going to render a cube on a black background. We're going to animate that cube, watch it spin. We'll look at it with a flat shader. We'll look at it in wireframe. And this will go pretty quick. It's about 15 minutes here. What I have set up for the first demo, really simple directory structure, index.html, loads our JavaScript files. I've got a JS folder, the ext external JS. That's where we have Three.js and 3 modules. I put my code in main.js. I'm sure there's a lot of people rolling their eyes right now. I don't want to get into JavaScript convention wars. And there's also a run.py. We're going to use that later. But all run.py does is starts the Python simple web server. And we'll talk about why that's needed later. I don't know if you guys can see that on the screen. I may open that in the editor. And in fact, we may have lost, we lost a lot of resolution here. I guess it was the switch for the screens. 1 second. Get it back. Hey, that looks a whole lot better. Right. Oh, a little bit easier to read. But basically, I'll walk through the lines really quick. I won't waste a lot of time. I've tossed in some console logging, so just when we have our web page open and we look at in the console, we can see what our code's doing. It's how I write a lot of my code, print statements and console logs, just to understand what's going on when I'm building it. Most important thing, first thing we have to have is a scene. Again, that's that collection of all of our 3D stuff. And then we have to have a camera that we're going to look through, and that's the rendering. We'll render the scene through the camera. So we've got a couple statements in there. We say, hey, we've created the scene, our JS file's loaded, the renderer has been created. What we have access to, if you can see, we declare the renderer variable on line 7. We're saying that's a WebGL renderer. Three.js has a couple other options for renderers, but WebGL is going to give us access to the GPU. It's going to do better shadows and lighting. So that's what we're going to use for this project and for the demo. And that gives you a DOM element, so you just inject that on the page. Very easy. If you've used jQuery, you're going to be totally comfortable here. And I think that's Canvas by default. Somebody can correct me, and we can look at the source after it loads. The next few things we do is we declare some geometry. So we make a box, which is called box geometry. We make a material so that we can shade that box. So we make this green basic material, and that does not interact with lighting in any way, so we don't have lights in this one. And we make a mesh, and the mesh is just taking that geometry, putting that material on it, and then we add our cube to our scene. All of this stuff's in the global namespace. We'll talk about pros and cons to that. Obviously, this is not great if you're going to ship something out, but it's helpful for this demo because we can play with things through the console. And then finally at the bottom, we reposition the camera so we can actually see the cube. If we don't move the camera, everything starts at origin, 0, 0, 0. And so our camera would actually be inside the cube. So we just back the camera up, and we have this render function. This is the completed version of the code that we're going to get to in the next couple steps. But the cube, we do some rotation. So all we're doing is incrementing the rotation value on the X and Y axis, which will cause that cube to tumble. And there's a request animation frame call in there, so that's going to get called over and over and over. I think by default it's 60 times a second. And then we call render on our scene. So we say render the scene and the camera. So jump right into the demo. I've got that open right here. We'll refresh the page, and we're all blown away, I know. Black screen. So what we see, I do those console logs. Main.js is loaded, scene and camera was created, the renderer was created, and the DOM was modified. What you don't see here is there was no cube added. So if we just step forward, let's see, let me bump this up, just so everybody can see what's going on. Using an app called Get Presenter, it's pretty cool, lets you step through your commits. So now we've added a cube. we can see over on the right-hand side, the cube was created, the camera was repositioned, and we started the render. Doesn't look super impressive right now, and doesn't actually look like it's 3D. This could easily just be a DOM on a black page, or not DOM, a div on a black background. And so what's kind of cool, I was hinting at, having access to these from the console, is we just have this global variable called material. And one of the properties of a material is whether or not it is in wireframe mode, so it's currently false. So we can flip that to true. And we can see we actually have a 3D cube. So one of the mistakes I made on purpose was I put the animation code in the wrong place. So if we did our cube rotation outside of the render function, what we end up with is one slight skew of the cube. So if you noticed, it's very subtle, just now the edges are kind of jagged. And if we once again flip over to wireframe, we can see that cube's been pushed over a little bit. So the correct thing to do there would be to put that cube, or put the animation code in the render function. So that's being called over and over and over. And we have our nice tumbling cube. We can turn on the wireframe, see what that object's actually doing. Let's see, I brought some demo notes to make sure. Yeah, so showed off the wireframe. I'm sure at this point everyone is super excited and can't wait to get back to your computers and make cubes tumble in space. Most likely, if you're going to do anything with 3D, you're going to be communicating something visually. And you can communicate things visually through animation. More than likely, what you're going to communicate with is a model. And so I went on turbosquid.com, that's a 3D model repository, and I grabbed this model. It was a free model they called a digger, excavator. And we're going to talk a little bit about what it takes to load those custom objects. This was the first big gotcha for me. So I come from a background with 3D graphics, and I use a software package called Maya. And never really, I've not done anything with games, and rarely do I have to deal with issues with what my objects are made of. And we talk about that, we talk about the polygons and the edges that are in place. So if you notice on the top left, all of the faces or all of the planes, they're all quadrangles, they're all squares. It's generally what you want. It's nice, clean geometry. Doesn't work with Three.js. Three.js, your objects have to be triangulated. So if you notice the difference in the top left and the bottom right image, there's all kinds of diagonal lines now. All of our planes have been triangulated, so every plane is a triangle with 3 edges. Not going to dig into why that matters and what that means, but it did increase the complexity of our geometry, and that's important to know. So when you start talking about really big models, you're storing more data points now. And when you store more data points, when we pass around these files, these OBJ files, that's a text format, the files get big. And our first run on the Capitol dome, we actually had the whole Capitol. We didn't just have the dome. And we were well over 200 megabytes. So sending 200 megabytes over the internet to load, not so great. And a real quick sidebar. For this, I went through from scratch on these demos to make sure I didn't tell you anything wrong. There are scripts that will triangulate your geometry, but you don't have a lot of visual control over the output of those scripts. You kind of just have to like fire them off, check it, fire them off, check it. You can download Blender. It's a free 3D software package. I'm sure that's kind of jumping in the deep end. I'm very comfortable with 3D programs, so I just grabbed it. It was free. It took me about, I don't know, maybe 8-10 minutes to Google around and figure out how you do a triangulation modifier. But that's what we did. We took Blender, and in the sidebar in Blender, you have these modifiers for geometry, and we just say, hey, triangulate this for me. And the default settings worked just fine. But the thing about using a 3D package, 3D software package to do that is you're going to have a lot of detail and fine control over the methods that it's using. We can talk about that. With really complex geometry, potentially it won't triangulate cleanly. So the very next thing you do, so we've triangulated our OBJ file. So we have this new OBJ file. It's a little bit bigger because now it's triangulated. And you can load OBJ files with Three.js. I've never had it work correctly for me. So last year when I was in the middle of this project, and we're going to talk about the timeline for this towards the end. I was in the middle of this project and I can't get the Capitol model to load cleanly. There's a script that they provide, and I know that text is really small on the screen, but it's clickable in SlideShare. They provide this Python script that's called convert obj3.py, and that will take an OBJ file It will convert it over into a format that it knows how to read natively, and it'll output that wrapped up in a JSON file for you. So again, if you've used jQuery, if you've used anything else where you've dealt with JSON, you get a JSON loader. It has an onload callback, and it's pretty simple for all things given once you've got the tool chain down, once we get to this point, to load that code. So even with some ample comments there, 16 lines of code to add in the loader, and that's with me breaking the lines to keep it readable. This highlights one of the changes I made. I changed the name of the material from material to green mat. And we'll talk about why that is. We're going to introduce a couple more materials here. We'll move on to demo number 2. It's where we initially add it. So, now we have a problem. So if you can see in my address bar, I'm just loading the index.html file off disk. This no longer works because when we go to use the JSON loader, it's doing an XML HTTP request, it's doing an AJAX request, and those don't work so great across file URLs. So, type straight. Have this really simple run.py script. Again, all it does is launch a web server and serve forever. So we'll run that, and we'll go to localhost 8000. And now we have some geometry loaded, and I think if you remember the first thing I touched on, if we don't move that camera, if we just threw a cube in and threw a camera in, we're actually inside the cube, and we didn't see anything. In this case, our geometry is pretty big, and I've put an animation on it, so it's rotating right now. So what we're seeing is the camera is kind of clipping in and out of the geometry. How do we fix this? Who's got an idea on what we can do? Back the camera up? What else could we do? Okay, make geometry smaller. I made the geometry smaller because I didn't know. I thought, well, I can move the camera, but then things start getting complicated. I don't know how big the model is. Another brief sidebar, if you use Blender and you alter your geometry in Blender, you can actually change the scale of the world or the scale of the object in Blender, and it'll load in smaller. So again, there were no right or wrong answers there. I chose wrongly, and we'll talk about why that was wrong, to change the scale. Actually, before we move on from this demo, again, everything's in the global namespace. I guess I don't have Digger on here. Let's look at so we have our scene. Scene has children, and we see the one and only item in scene.children is mesh. So if we grab the first child there, and we can set a scalar value for the scale, so that'll just scale everything uniformly there. We can scale that down. And I thought, hey, yeah, that's the way to go. I scaled that down. I can actually see what's going on. Again, it's a flat shader. It's kind of boring. If we look at, I changed this variable name to green mat. Again, oops, not wrap around. We want wireframe. Kick on wireframe. We see a little more detail, see that the object's there, and rotating around. So kind of, let's see. We'll pause there. We'll say that was that demo, because we're jumping ahead a little bit, lighting and shadows. So you saw the green, flat render. We turn on wireframe. We can actually see the details. We can see the geometry moving. You got a sneak peek there in the red where we could see a lot more detail, see the object moving, and that's where we get into lighting and shadows. It's important to note that the red color that you're seeing, those aren't shadows when you kind of saw that thing rotating a second ago, and we're going to come back to that. For the demos, for this, there's many light types. There's point lights, spotlights, area lights, hemispherical lights, and what we're going to talk about is directional lights. Directional lights are like the sun, so that's parallel rays cast from some point that appears to be infinity as far as how the visual look goes. Technically what happens, the same way our scene looks through a camera, we call that a perspective camera. If anybody ever did art classes in high school or college, you may have taken a class or a demo where you do a 2D perspective drawing, and you take a ruler and you make 2 points way out, and you draw all your points. If this line goes left and to the back, you draw off to these points that kind of simulate things going back into infinity. Perspective cameras do that for us. What happens with a directional light is we have an orthogonal camera, and that's what you see, this gold box or the orange or yellow box. That's actually a camera, so it's a viewport for that light. And when we calculate shadows, it's only going to calculate shadows for efficiency and speed with what it can see within that box. The other technical word, we talk about camera frustrums. I've heard that. Frustrums? Frustum, there's no R. I didn't put it in here because I was like, we're going to go way too technical. But that's what that is. That's the camera frustum. So it describes the camera's field of view. And so it gets a little bit complicated, but our shadows are casts in what the camera can see. And as far as what an orthogonal view would be, if you've ever seen mechanical drawings, you see a top-down drawing, it's going to have a 2D look to it. Important thing to note, Three.js, when using WebGL renderer, it does shadow mapping. If you've heard the term texture mapping before, if you think about mapping anything, that's when we take something and we apply it to a surface. So what's actually happening is the shadows are being calculated, and then at render time, they're being applied to the surface. The shadow map is a matrix for the way that we will access it and talk about it, and that's a buffer. So the larger the matrix, the larger the buffer, the more information we can store about the shadows in a given area. The scale of your models, the size of the camera. So if you look way off in the background, you can kind of see those orange lines. I don't have a cursor on here, but coming just off the top of the arm of the excavator. So we've scaled that light's camera way out, and our whole scene now fits inside of that. And that's how we're able to cast these shadows. This was about, I think this was 4096 by 4096, and for the size of the matrix. And you can see there's really fine detail in the shadows. So all the hydraulic lines going up the excavator arm, they cast a shadow down below. Does anybody, and I'll ask this question in a second, does anybody see anything weird about this right now? Keep going. Good. All right. Nobody saw my mistakes. So I kind of got ahead of myself a second ago. So we've got this demo loaded. Obviously, I blew the dust off some code, and they've changed the interface with Three.js. So the code still worked, but there's lots of warnings about how they've changed things into dot notation and put them in an object hierarchy. But everything's still working. So we have this material now that's not the green material, and we have a light, and we don't have the light visualized. But there's actually no shadows right now, and that's important to note. When you see a dark side of the object, that's just the shader is not interacting with the light, so it doesn't render a color there. So no shadows, only shaders at this point. And so we can look at a few different things. We have our lights. We have access to our directional light in the console. And we're just going to turn the light off. Oops, if I can type. So we turn the light off, the object disappears. If we turn the light back on, object is still there, still rotating. It's just there was no interaction for that shader with the light. So if we again flip that off and we swap out the material, so now we have access to the digger. Digger has a material. When you see it has a mesh Phong material, not going to get into that, that's named after it's a guy's last name. So there's Lambert shaders and Phong shaders, and those all describe how light interacts with the surface. And a Phong material kind of gives it that metallic or kind of gives it a sheen on it. You can describe surface roughness and things. But we'll just flip this back over to our green mat. So once again, we see our digger. The light's still hidden, the digger shows up. That's important because this is a very simple shader. The shader does not think about interaction with lighting at all. So these are important concepts to keep in mind because it's not a lot of overhead here. If you wanted to render some very basic things, you don't care about shadows, you don't care about shading, you can just throw a simple basic mesh shader on something, render the object, or even just render it in wireframe, and you're good to go. And then we can switch this back to the red Phong. It doesn't show up again, and turn our light back on. So again, no shadows yet. So we'll switch to my next stage here, and now I've added a ground plane, and I've moved the camera. So I saved us from a big mistake I made, but I'm simulating that mistake. The mistake I made was if everybody remembers, I scaled the digger way down. I scaled it down 0.01. The shadow map did not have enough information, and the scale was so small, the camera was too big. The camera for the light was too big, and I was getting really bad shadows. So to save us from enduring all of my mistakes and just kind of hopefully giving you something you can take away from this, The model's been scaled back up, the ground plane's been scaled back up, and the camera's been moved way back. So if we want to see where the camera's at this moment, we can look at the camera position. So we're 250 units off and 250 units up, which gives us this kind of 3/4 view. But those shadows are pretty ugly. Does anybody gotta know what we should tweak? Shadow resolution, that's right. And you know, I don't know if you've done this before. Again, I just want to have a conversation. I mentioned this word, but I mentioned it in passing. Do you know what the shadow resolution is controlled by? It's okay. No, okay. So that's where I was talking about, we have shadow map shadows. So if we change the size of the shadow map, we're going to alter the resolution of that. So we'll mess with that now. If we take a look at our light has a shadow. And so that's a directional light shadow. Again, that's ultimately a camera. We have a map. And we can see there in the properties, the width is 256 and the height is 256. And it comes with a helper for set size. If you don't use set size, the changes you make don't appear immediately. So we're actually going to turn it down first. So we'll turn it down to 128. Now we lost a lot of resolution, a lot of fidelity of the shadow is gone. Let's crank it way up. Let's go 4096 for both of those. And now we get those really nice, crisp shadows. The larger that is, the more memory we're currently using now, and the longer it takes to process because the shadow is so detailed. So ultimately, you're going to want to look for some value. We can try 1024 may be enough to give us the resolution on that. 1024 is not bad. There's always a performance trade-off when you tune these things. So that's important to know. I still haven't done something right. Does anybody notice anything weird about this? Sure. Sure. I'm going to come back to you because through the microphone I'm going to repeat so anybody watching online. He said the shadow's too stark. It's too dark. So we would do some transparency, work on tuning the shadows. So that's good. What did you say? So the shadow doesn't cast onto itself. Bingo. The shadow doesn't cast onto itself. And so I skipped a lot because I just wanted to kind of show you guys this stuff. And what happened is, we'll pop over and look at the code really quick. When we do shadows, we have to tell which objects cast shadows and which objects receive shadows. And so we notice that the ground here on line 79 has a receive shadow true. And if we look back at where we load the excavator, oops, yeah, there we go. Sorry, the light's casting a shadow, not the excavator. So anyways, the excavator has to be set to receive a shadow. So it's like these little gotchas. I ran into all this. I'm like, why are my shadows not showing up? Oh yeah, I have to actually tell it to do that. And so that I don't mistype this, I have this ready to go. Here we go. Receive shadow. And I don't know why it doesn't show up until you refresh the light, but if you turn the light on and off, then those shadows show up. So the details that we're looking at now is you see the arm cast a shadow across itself. We see the hoses cast a shadow at the bottom of the arm, and even that little grating where the exhaust pipe is, the grating is receiving a shadow. And what's pretty cool, if we go in here, it still casts shadows in wireframe mode too, which I thought was very interesting. It was a really cool visual effect. So that's how I did the screenshot for the beginning of the presentation. So I'm going to push pause right here because this is kind of the end of like Three.js tutorial. We're going to move on. Did anybody have any other questions, comments, concerns? Yeah, the easy fix for making it not cut through the ground is to level the ground plane. I have the ground plane tilted up towards the camera and doing the intersection on purpose, and the demo that I was going to do with that didn't work out and I just didn't fix it. So that's what that is. Yeah, the ground plane's not level. Anybody know what a quaternion is? Do you actually understand them?
I understand why you need them.
Sure, gimbal lock, right?
Yeah, well, yeah. And like a...
Sure.
What's it called when you...
I don't remember. So setting the angle, that was all I was going to say. Setting the angle, there's a few jumps you have to do. and I just backed out of it. If you're very comfortable with quaternions, you can just plug the values in and it'll flip over 90 degrees and be exactly what you want. That has a rotation value of 5, and I can't tell you why it's 5 because it's all things I don't grok. And I ran for the hills when I got into all that. So that kind of ends the Three.js part. I want to talk about the Leap motion controller. So I brought that with me. I've got that over here. Show of hands, anybody's heard of a Leap motion controller? Most of the room has actually used one. Are you still using it? No, okay, it's kind of, I mean, I don't work for them. It's kind of gimmicky, but it's neat as well. So I've played with some of their demo software. It was super easy to integrate with Three.js, and we're going to talk about what they give you. They have a tremendous developer support out of the box with their libraries, but it is a bit finicky. And so what I've got, the first thing we're going to look at, we're just going to open the visualizer. And so there's 2 cameras in here, 2 infrared cameras, so we can kind of see me there. It's doing depth sensing, and what's neat is it can detect the difference between your right hand and your left hand. It knows if your right hand's upside down compared to a left hand. So it's pretty smart. And it tracks your arm, and you can see you have access to these bones. So any of the fingers, like it's got pretty good resolution on finger bends, gripping motion. But if you move fast, so I flip my hand over there, you can see the video sees my hand flipped over, but the 3D model still hasn't caught up. If I open my hand, then it kind of snaps over. Now when I've closed my fist, it knows I pulled my fingers up, but it doesn't realize I've made a true fist. So you have access to all of this data and information through their API. So there's other things we can look at. You can tune the interaction height. So that's the height above the sensor where it expects hands to be. Before we got started, and I'll open that just so everybody can see what I've tweaked. I changed the interaction height to about 19 centimeters. I don't have hard and fast rules for why that is and why that value works, but that's what I set it to, and we'll see how it plays out when we load our demo. And so what happened, again, we're going to go back to what I touched on at the beginning. Last spring, my old boss from the Washington Post says, hey, I've been talking to everybody, the old crew back at the Post, and they're going to do this really cool interactive exhibit for the White House Correspondents' Dinner, for the big reception. And what you're seeing here, the picture on the left, is the final product. That was 1 hour before doors opened. And so they built, you can see in the background, there's like this 7 or 8 foot tall, maybe even taller, cutout of the Capitol dome. And then you can kind of see, I cut the picture off, but you can see there's our 3D model there on the left-hand side, and we built this custom arm that holds the Leap controller out. So you're standing back away from the screen, and you're interacting in 3D space with this 3D object. It's very novel. That was not the original intent of what we were going to demo. We were going to demo the Washington Post homepage, and the header was going to have this 3D object. We were going to use gesture detection to have you kind of jump in and out of the 3D interaction. It got very complicated very, very fast. So you can teach it custom gestures. You can look at like what position fingers are in. If you use their built-in gestures, it works a lot better. So we were trying to do gestures like rotating clockwise. So if you made a finger and you pointed out and you rotated clockwise, that would exit the 3D visualization. And if you rotated again, it would scroll down the page. And then there were sliders on the page. So if you made a fist and you would move the slider up and down, it would move things around. And we had all of this planned out. The interaction designers at the Post are stellar. We had wireframes and everything, all this interaction mapped out. Extremely difficult, and we had about 3 weeks to do it. So Three.js ended up with the Three.js with Leap. We were able to do all this in a web browser. Somebody on the Slack channel, and sorry I don't know faces to names, mentioned that for their 3D stuff they use Unity and C, and I know what Unity is. I hate C and C++. I would probably like it better if I did it every day. But obviously JavaScript, much more approachable. So we were able to deliver this on a pretty tight timeline, given that I knew 3D graphics and I knew JavaScript, but I didn't know everything in between. So I've got a video of a very early prototype. So you can see what's going on here is the rest of the web page was down underneath. There's my favorite thing ever, the console open, echoing out all the stuff it's doing. So we'll watch this video. What we initially wanted to do was have the hands be locked to the 3D model and what we kind of called gimbal controls. And this was before there were any sort of limits put in place on the gimbal motion. And so it just didn't work very well. It was sort of intuitive. If you waved your hand, it would rotate the model. If you swiped, and in this case, you're not seeing, it doesn't detect the actual swipe gesture, but if you swiped, it would spin the model, and if you made a fist, you could kind of lock the model and turn it. Very Iron Man, you know, it was really cool. It was way over my head. I could not figure out how to make it work, and that's where I got into quaternions, and you have access to the motion. We have access to all those points, those bones and skeletons that you saw in the visualizer with the hand. And it's how do we say that this hand exists in 3D space, and I want to translate that motion into a model in 3D space. And it got really complicated really fast. I don't have a degree in physics. I have a degree in like special effects animation. So if they wanted like it exploding and throwing particles, I could do that. So ultimately, we had about 3 weeks to deliver this. And so it chunked out pretty well. We spent about a week on the interaction. The majority of our time was trying to make that gimbal motion work. The next week, we spent on rendering and lighting. Shadows were a pain. One of the things I skipped, excuse me, just 1 second. One of the things I skipped on shadows, and I don't have an example set up here, is there's a concept called shadow bias. And there's an artifact called shadow acne. And so if you look into depth map shadows in any great deal, there's all sorts of artifacts that show up as light passes through and around things that would cause striations and patterns. If everybody's seen a Gaussian pattern before that's cast out, you run into all kinds of problems and artifacts. And tweaking the shadow bias will correct some of that. And so what you'll see in the demo is I never really solved the shadow problem. I got it to like best look, and we moved on. Because again, we were now down to the last week. So we had stripped away all of the functionality of the web page. We were solely focused on building this 3D interactive kiosk, and you're now supposed to somehow get information from this kiosk. As you explore this model, you're supposed to find information about the Capitol Dome. What was really cool about that was you can just use HTML inside Three.js. It makes it super easy to translate coordinates between 3D space and 2D space, so we can have pop-ups pop up on the screen. It was a little buggy. The amount of time we had to work on this and build this, we were able to skip a lot of stuff, a lot of things we didn't have to worry about. We had a very controlled environment, and we had someone there showing each person that would come up and say, hey, yeah, this is our interactive experience. It's, you know, you're gonna like interact with this 3D model. So shipping this to just a user out on the internet, I can't say for sure how well or how successful this would be. I'm not advocating that the solution I found works that great, but nevertheless, it is something. Let's kill the console, give this a refresh. So we're loading about 200 megs right now of object data, and that's off local disk. That's not even calling out. So it takes a second to parse that much JSON, and now we have the object loaded. Stand back for a second. I'm hoping it didn't detect my hands. One of the things we thought about was like, this is kind of boring. So if this is just on a screen and people are walking around the room, no one's going to walk over to this. Like, it looks like something's broken. So there's a demo mode. This thing automatically goes into demo mode if it doesn't detect any hands in 15 to 30 seconds. So there we go. So now if somebody walked away from the kiosk, you kind of get this visual interest of like, oh, hey, what is this thing? There's something spinning around. And what I wanted to talk about in demo mode was the type of animation that you see taking place. We move the camera and we move the dome, but we don't ever, you'll see when I interact this, we don't ever let the user do those two things at the same time. Again, things got really complicated. So what you're seeing here is that dome is spinning and we're translating the camera up and down and in and out, and we get this nice, cool pan, and those are all scripted points because it knows everything in space, so we're moving the camera over and doing this. And so as soon as a hand shows up, it'll come out of demo mode. And so we have two hands in here. You can see, this is what I was talking about. I didn't model those hands, so you just get that from Leap, their JavaScript library. And they have a great integration with Three.js. So I was like, hey, I want my hands to show up. And it's literally like 4 lines of code. My hands show up. So we're just focused on using one hand. So the other thing was, okay, you've got the hand in here. The origin, I didn't have good notes. I look back at my technical notes, and shame on me for not keeping good notes on the problems. And we'll look at the code in a second, but basically the origin of where this hand is changes. And so we know where it's at in world space, but you have to translate that from space where the sensor's picking it up. So sometimes if the hand pops in different places, it doesn't match one-to-one. And there you can see the hotspots showed up. So if we intersect, it's just using very simple ray casting, if you're familiar with ray casting. I found it on Stack Overflow. I wasn't familiar with it, but I know a lot of JavaScript games are using that for wall collision detection. So all we're doing, we're just saying, okay, if the hand intersects any one of these spheres, we want to show this little hotspot information. So if you notice that hand, sometimes it'll turn pink. So the control scheme we came up with was this like fake joystick. So again, if you kind of turn your hand sideways and just pinch, and we have basically a joystick. So we can move our hand down, which will move the model up, or move the camera up in relation to the model. If we make that pinch motion again and we go left or right, and again, this is where it gets into kind of the finickiness. You can rotate. The further away you get, the faster it rotates. And we can look at the code how that's doing that. It's very simple. Obviously, why it was the solution, I could actually comprehend and understand what I was doing here. But the further you move away from the origin of when this pinch gesture starts, controls how fast things move. And so we can go left, right, in and out. So let's see if we can zoom in here. There's actually quite a lot of detail to this model. You can still interact with everything. The one thing you'll notice, the hand scales. So we're doing an entire world scale. There were a couple options we played with. We played with keeping the hands the same scale the whole time. Guess what? It was really complicated. So it was a reoccurring theme with this project. I'll switch back over, let's see, because I don't want to run out of time. I've been going pretty long here. I want to make sure I hit this, that I put the thank you in here, and I'm on Twitter, at Lee Trout, in case anybody needs to jet. I'm on the Cha Dev Slack, but I'm popping in and out. So we can flip it over to questions. I can hang around if anybody wants to play with this. You can come up. If anybody wants to look at the code, before we completely wrap it up, I'll see if that pinch gesture. I split my code up. I kept everything. Actually, let's see. Do two demos really quick. It probably didn't resize correctly. I have a namespace set up. So we have _3D. And this isn't great for sharing with people because, like, what do all those things mean? So I have 3D, I have X, D, and P. X is this command and control system that handled all the loading for us, so we didn't try to do something before something else was present or not. Then we have D. D was the 3D object, and then P was the leap motion itself. So if we look at the 3D object .D, we have the 3D namespace, and in here it just has this default X variable that's holding all that. And so then we can start to see the things that I'm tracking, whether or not pinch has been activated, what's active, if a hotspot's active, and then we have access to our ambient light and our camera. And so in the code, that's split up into CNC, command and control, which handles all the loading and starting everything up. We have another file called leapoffaith.js because this was a big leap of faith using leap. And there's things in here. So I've set everything up as basic classes in JavaScript. So we have this pinched. So this.pinched is false. And then this is where you set up using the rigged hand. Again, I didn't write in this code. They give it to you in the developer documentation. You'll see a lot of extra stuff in here. Page scroll up, page scroll down. Those were all things from when we had the dual interaction going. And so here's how the pinch check is actually ran. And so we're basically, I use _ liberally, and I got away with a lot of bad habits. So a lot of the animation and things that you see taking place, they're all done with the throttle function in _. So there were better ways, but again, short amount of time. So the pinch check loops over each hand and then looks at the property of that, and if it detects that there's a pinch strength, so it thinks the hand is pinched or grasping. And so we have these watch for pinch functions, which just have a set interval. So a lot of things very basic. You could certainly get more elegant and more complicated in the JavaScript, and definitely more efficient in detecting a lot of these motions and stuff. But I'll stop talking now. And that's pretty much it. It was a blast to do this project. I essentially got paid to learn Three.js, which was awesome. Those are always the best projects when you get to learn something cool and get paid for it. And ultimately, it was a big hit at the show. Anybody could walk up and interact with it. You know, we did have someone there that explained, imagine you're holding a joystick, and this is what you do. Be patient. But other than that, it worked really well. I hope we get to do another project like that in the future. But that's pretty much it. So thank you all. I really appreciate it.
We're right at the edge of things here, so if you guys want us to stick around and talk to Lee, do so. Give him another round of applause. Coming down all the way down from Jonesborough.
Thank you.
Sick to boot. Incredible, great presentation.
Thanks.
Next week we've got Sam coming at us. He's works at TVA as a software engineer and a BI expert, and he's going to be talking to us about Power BI, which is a Microsoft data visualization library. Is that the right? The library. It's a whole service. It's a whole ecosystem, if you will. So come